let's dive into this video. EGDMA stands for ethylene glycol dimethacrylate. Picture it as a molecule with two active arms. These are methacrylate groups. When EGDMA meets another group with reactive site, it forms strong, durable crosslinks, like a molecule handshake. This crosslinking is the key in making materials tougher and more resistant. Now let's talk HEMA, hydroxyethyl methacrylate. This molecule has a special group called hydroxyl group. Think of it as a water magnet. When HEMA encounters water, the hydroxyl group grabs into water molecules, making HEMA highly hydrophilic or water attractive. So, in a nutshell, EGDMA builds strong networks through cross-linking while HEMA loves to mix and mingle with water. Together, they create materials with unique, useful properties. Traditional drug delivery have their flaws. Poor encapsulation, uneven release, you name it. But there is a game changer on the horizon: copolymers. So, what are copolymers? Simply put, they are molecules made from two or more different types of monomers. Think of them like custom-built Lego sets for medicine. Here's how it works. First, we prepare these copolymers via a process called inverse mini-emulsion polymerization. It's like cooking up a special recipe where the ingredients mix perfectly. Next, we establish correlation of synthesis parameters and resulting properties. Finally, we dive into a comprehensive analysis of these copolymers. First step, we mixing aqueous and oil phases. Next, we move on to sonication. This step uses sound waves to break up particles in our mixture. Sonication ensures those particles are evenly distributed. Onto the main event, polymerization. We're doing this in nitrogen atmosphere to keep things stable. Just set your reactor and let magic happen. Once polymerization is complete, it's time to see what we've got. We'll use FTIR or Fourier transform infrared spectroscopy to identify the chemical bonds. TGA or thermal gravimetric analyzer helps us understand the decomposition points. DSC, differential scanning calorimetry, measures heat flow and tells us about material properties. For visual check, we've got SEM, scanning electron microscopy. This gives us a super detailed look at the surface structure. And finally, we use contact angle meter to assess how our polymer interacts with water. Each of these techniques reveals the piece of the puzzle, helping us understand and perfect our copolymers. Here is some analytical techniques: FTIR, TGA, DSC, SEM, and contact angle measurements. First up, FTIR spectroscopy. The FTIR spectrum can highlight peaks from different function groups. For example, we will spot peaks for C double bond O in OH, but notably no peaks for C double bond C. This tells us a lot about our copolymer structure. Next, let's talk TGA or thermogravimetric analysis. It measures weight loss as we ramp up temperature. From TGA, we can see how cool different mole ratios affect thermal stability. TGA graph shows weight loss of copolymers at various temperatures. This helps us pinpoint the decomposition temperatures for each decomposition. TG or glass transition temperature, where is DSC comes in. DSC thermograms show us the TG for different polymer compositions. It's crucial for understanding the thermal properties and behavior of our materials. Now, onto SEM or scanning electron microscopy. SEM images gives us stunning visual of the copolymer surface. In our case, we see spherical nanoparticles, which could mean exciting applications in nanotechnology. Finally, contact angle measurements. By placing water droplets on the copolymer's surface, we can gauge its hydrophobicity or hydrophilicity. Next part, we get to know how mole ratio could impact our copolymers. We compare ratios from 1:1, 1:2, 1:3, 3:1, and 2:1. Firstly, glass transition temperature or TG. Higher ratios like 1:3 and 3:1 show better thermal stability, meaning they can withstand higher temperature without deforming. Next, we have swelling behavior. Lower ratios like 1:1 tend to swell more. This means they absorb more liquids, making them less stable in wet conditions. What about contact angle? This measures how water interacts with surface. Ratios of 2:1 and 3:1 have higher contact angles, meaning they repel water better and stay drier. In summary, more ratios help in choosing right material. Ratio depends on what properties